In this session, we will look at Fleming's left hand rule and its applications. Fleming's left hand rule is a very useful and a simple rule that will help us understand what will be the direction of force on a conductor which is kept in a magnetic field in which there is current flowing in the conductor, and this is exactly the Fleming's left hand rule. This indicates the direction of the current, this indicates the direction of the magnetic field, and because of this current carrying conductor placed in the magnetic field, it will experience a force that is given by the thumb. That's it. That is Fleming's left hand rule. Now let us look at applications of this. First of all, I will draw this here as a reference. This is one direction, this is another direction, and this indicates an arrow coming towards us. So if we hold it like this, right? So this is the direction of the magnetic field, this is the direction of the force, and this is the direction of current in a conductor. So if there is a conductor like this, this is the direction of the current in the conductor. So this is how we go about applying Fleming's left hand rule. Let us look at the first example. Suppose there is a magnetic field in this region towards right hand side. There is a magnetic field in this region and there is a current carrying conductor. Assume that this pen is the current carrying conductor and it is facing exactly towards you like this. So it is right towards you. So you can't see the length of this conductor, you just see only the tip of this. That tip is indicated with a circle and a dot. It means there is a current carrying conductor with current coming towards you. So this is the current carrying conductor. This is the magnetic field. Now what will be the direction of force acting on it? You take your left hand and keep the three fingers mutually perpendicular to each other. The middle finger should be in the direction of the current. The pointing finger should be in the direction of the magnetic field, and you see the direction of the thumb that gives the direction of the force acting on it. So the force acting on the conductor will be in this direction. This is how we apply Fleming's left hand rule. Another example, because we need to do a couple of examples to get it right. Another example, I will clear this first. This time let us take a magnetic field going inwards. Circle with a cross. Circle with a cross indicates that there is a magnetic field going from your side into the plane of the screen here. So this is the magnetic field, in which let us assume that there is a current carrying conductor. Let us take the conductor to be in the vertically upward direction. So there is a wire like this. I will just cut it short a little bit. Yeah, there is a wire like this which is carrying current in the upward direction. Our job is to find out the force on this wire because it is placed in this magnetic field. Again, the Fleming's left hand rule, the three fingers are ready. This finger should be in the direction of the current, right? So this is fine, but look at the direction of the magnetic field. The pointing finger, the way I have pointed it, it is towards right hand side, but the magnetic field is inwards. So what do? Keep the direction of the current same because you have fixed it now. Turn the direction of the magnetic field. Now you see this finger is pointing in the direction of current. The pointing finger, you won't be able to see that because that is going into the screen, right? That is the direction of the magnetic field. Now this is the direction of the force. So the force acting on this conductor will be like this. Like that, you can choose any directions, right? We have chosen two different things. Let us take up another example. I will clear this. Let us take magnetic field in the upward direction. Let us say that the magnetic field is upwards like this and the current is inwards. This is the current carrying conductor. The current is inwards and this is the direction of the magnetic field. Now we will find out what is the direction of the force acting on this conductor carrying current I when placed in a region of uniform magnetic field. Again, the Fleming's left hand rule, all the three fingers mutually perpendicular to each other, and we have kept it ready. The direction of current should be inwards. So this is the direction of current, this is the direction of magnetic field, this is the direction of current, and the direction of the current should be inwards. So I come this side, you see the direction of current is inwards, but this magnetic field is not in this direction, it is in the upward direction. So hold the direction of current and turn it like this. So the direction of current is inwards, this is the direction of magnetic field, this is now the direction of force acting on the conductor. Now, we have seen three different cases where we have identified the direction of force acting on a current carrying conductor when placed in a region of magnetic field. One very interesting application of that is, how does Fleming's left hand rule render itself useful for a single charged particle? Let us understand that. Because when I take a conductor like this, when I say that the current is flowing in this direction, basically what it means is fundamentally there are millions and millions of charged particles moving in this direction. So if there is a force acting on the conductor, it is actually because of force acting on each individual moving particle in that conductor. That is what gives rise to the net force. So let us understand, how does a particle move if it is just a single particle in the region of magnetic field. I will clear this. Let us say that there is just one particle of charge q and mass m moving with velocity v, and it enters into a region of uniform magnetic field B. This is the region. And I will draw a dotted line to indicate that the field starts from here. This is the region where the field starts. So the charged particle comes up to here, and up to this point there is no force acting on it. Up to this point it will just move straight. But what happens here? If the charged particle is moving like this, it is as good as saying that the current is in this direction. The magnetic field is inwards. Fleming's left hand rule. The current is in this direction. Magnetic field is inwards. So turn it like this, and now you see what is the direction of the force? It is upwards. So the charged particle wants to go like this, but there is a force in this direction that will make the charged particle come up to here. Now the charged particle is here, and now the velocity is in this direction. This is the direction of the velocity. Again, Fleming's left hand rule. The direction of current is the direction of movement of charged particle, but it is no longer like this. You see, it is slightly tilted. It is in this direction. But the magnetic field is inwards. Now you see the direction of force. That is also tilted. Unlike earlier case, it is no longer vertical. So now the force is acting in this direction. This will not allow the charged particle to move like this. It will make the charged particle come here. Again, if you apply Fleming's left hand rule, this time I leave it to you, you will realize that the force is in this direction. So that will not allow the charged particle to move like this. It will make it bend like this. Again, apply Fleming's left hand rule, the force will be like this. This will not allow the charged particle to move like this. It will come out like this. The resultant effect of all this is that the charged particle will move along a circular path. Let us take a look at that using this simulation. So here you see, this is the charged particle, and this is a positive charged particle having mass given some initial velocity in the presence of magnetic field. And you see, this is how it moves. Why does it move like that? Let us look at the force. You see the direction of force acting on it? Always perpendicular to the direction of motion of the particle. And let us look at the velocity. See, the velocity is tangential, the force is radial. Now what happens if you increase the velocity? What happens if you decrease the velocity? Let us look at that. Reload. Now I will keep all other parameters same. Let me just increase the mass of the particle. Let us click play here, and you see the particle is completing a larger arc. Earlier it had just turned here, but now it is making a larger arc. Why is it making a larger arc? Because the mass of the particle has increased. You might have learnt it in 9th class, and of course you will again learn it in 11th class also, that larger the mass of the particle, more is the inertia. Inertia is unwillingness of the particle to change its motion. So if it is a massive particle, it will take its own sweet time to take a turn, and therefore it goes off like this. Whereas if I decrease the mass, now you see it makes a sharper turn like this. If I keep the mass same and if I increase the charge, now you will see what happens. See, it is taking a very sharp turn here itself. The reason is because that force is very strong. What is the expression for that force? In your schools, you might have learned that is F is equal to QVB. It depends on the charge Q, it depends on the velocity V, and it depends on the magnetic field P. But the end result is that this is how the particle moves. What happens if the charge is negative? We can further bring it down. Now you see I have taken the negative charge, same magnetic field. as expected the particle will move down. So, you can, using the simulation, you can make the magnetic field inward, or you can increase it, it is inward, you can decrease it, make the magnetic field 0, or you can further decrease it and make it an outward magnetic field. So, you can change the mass of the particle, you can change the charge of the particle, and you can explore further using this simulation. Right. So, I hope you have understood now how Fleming's left hand rule can be applied to various cases. Thank you.